There we go. I decided I'm recording as a backup too, just in case. There's going to be no more classes lost. All right. So we're talking about IRT stuff, right? Big picture, what's IRT stand for? There's an easy one.
Item response theory.
Yeah, is it a theory?
Mm.
No. No more than like you have regression theory or ANOVA theory or anything else. But whatever. What's IRT for?
You get your A, B, and C parameters.
And D2.
Indeed, yes, forgot.
Yeah, but why would we want to have them? What's it for?
Would you? I feel like that's a loaded question, but it could be used for developing the most appropriate items for the most appropriate people.
That's a great answer. I was going for something a lot simpler. So yeah, so we what kind of items is IRT designed for?
I think someone already
Categorical.
said binary.
Yeah, binary. We're talking about binary, but categorical more generally, yeah. So when you have items that are supposed to measure one or more latent traits, and those items are binary or categorical, that's what IRT is for. Yes, and it also is a way to choose which items you would want to include based on what kind of instrument you're trying to build. The idea of customizing reliability to meet your measurement goals is what we're talking about today. So that was what Kayla was saying, right on the money there. It is a nonlinear model. It has to be a nonlinear model because we have binary options that we're predicting, right? Binary data shuts off. You have a 0 or you have a 1, and we're trying to predict the probability of having a 1 from the model, and that predicted probability has to understand it can't go above 0 or can't go below 0 and it can't go above 1. What's the magic thing that makes that happen? Give you a hint. Yes, I am a loser, but that's not what the L is for today. Yeah, it's our friend Logit and its cousin, Probit. Yes, those are link functions. They're nonlinear transformations of the probability that's being predicted that make it so that our linear model with a factor as our predictor can predict the logit linearly, which translates into a nonlinear prediction of probability. Yeah. Here is a slide that has an IRT model on it. So I'm on slide 31 of lecture 5. The A's, the B's, the C's, and the D's. We're going to be focusing on just the A's and the B's in this class. The C's and the D's are less commonly used in measurement and the social sciences. Those are more common in academic settings, of course. But we've got 2 parameters here for each item. Each item has a difficulty, that's B, otherwise known as severity, and each item has a discrimination, and that's A, otherwise known as slope. So B tells us where on the trait the item is designed to measure. More technically, the definition of B is that it is the theta level needed to have a 50-50 probability of providing a 1 response instead of a 0. A controls how related theta is to the item, where stronger A's mean stronger slopes. And there's a picture that goes with that. There we go. Here's slide 33. And I fixed the lines on this for what I wanted to show. So for instance, the blue lines here, both of those blue lines have the same B value. They have the same difficulty or severity location on the trait. So both of them take a theta of -1 to hit a 50-50 probability of getting a 1 response. They differ in their A parameter. So the light blue line has an A that's 1, That's what generated this curve. And the dark blue line has an A of 0.5. So for somebody with a trait level of -1, the light blue line with the stronger slope is a better item. So if I were to try and create, say, a short form of a test, and I wanted to choose between those two items, I would pick the one with the stronger discrimination. More slope means better relationship between the trait and the item. Likewise, for the pink items, they are situated at a difficulty level of 0, such that 50-50 occurs at that point on the trait, and the pinkish one, as opposed to magenta, is the one that has the stronger slope. Neither of these items, though, would be good for somebody who has a trait, say, of 2, because at that point, the difference in probability as theta increases is not very strong. So they would not be good indicators of that. And that idea corresponds to something called information that we get to talk about today. So the two parameters in the two-parameter model, as it's called, B is always there. A is the second one. And what is it called if I don't have a different A for each item? If I have a model that looks like this, for instance.
Rosh.
Yeah, that's our friend Rosh, otherwise known as the 1PL to the rest of IRT. And that is a very strict assumption that all of the items are equally discriminating. So the idea of tau equivalent, for instance, that's what a Rosh model is. And Rosh models can be extended to items that have that are more than 2 categories. We'll talk about that, I think, starting next week. So question from the chat window. Theta is not a slope here. What does it mean in the 2PL? So theta is actually the model predictor. Theta is the location on the trait of the subject. So it's a subject parameter. The trick with these models, though, is that theta is a random effect. So we don't actually estimate what theta is as part of the model optimization. What we have instead is summary characteristics for the distribution of theta. It has a mean, it has a variance, and in models with more than one theta in it, it has covariances, same as in CFA. So the slope describes how well theta, as the predictor, predicts the item response as the outcome. It's just that if you look at the equation for these things, it looks nothing like that. But what did I promise you was coming? I promised you this was factor analysis still, right? I promised you. And I'm hoping to get there today, but if not today, then Thursday for sure. Believe it or not, this is factor analysis still. This version of the model is rearranged to provide different information than what a typical intercept slope version of the model would provide, but it's algebraically equivalent, and we will get there eventually. So does that help answer a question about slopes and thetas? Okay, and so if these curves, let me show this again, if the lower end of the curve tops out below or above 0 rather, then you might need a C parameter, that's the lower asymptote. And if the right side, it doesn't go all the way up to 1, you can allow it to asymptote under 1 with a fourth parameter, a D parameter. So those are options for you as well. And you can decide based on adding them to the model, if it fits better, whether or not you would need them. Okay, so any questions on any of this before we dive back in?
I had a question at last class. I think you ended on, you just like mentioned that the GRE uses I think the 3-parameter model. Is that right?
Yes.
So I think this is just because I'm like trying to figure out in my head like why people use different models at different times, or like how this is different from other stuff. But is that because it allows them to like they can pick whichever items they want? They don't all have to be used at the same time. And then do they still use like factor analysis to figure out like dimensionality and that kind of thing?
Oh boy. I think the idea is that they're trying to get a test that's unidimensional because they're trying to measure like math, right? Or verbal as a thing. And so any items that would not well measure that single dimension would probably be removed.
And did they test that like with CFA?
Um, I think I'm not sure exactly what they do. I think you'd have to do some digging in the documentation. My guess is that they use item fit and person fit kinds of things to be able to uh, decide which items that they should keep. But they have banks and banks of items, and not everybody sees every one. But at some point, they gave a large enough sample, all of these items, so that they can calibrate them. The idea is that you would estimate what the A, B, and C parameters are for each item, and then you would choose which items to give to somebody based on those parameters. So I'm not sure of the more technical details in terms of how they go about choosing things. I do know that in order for them to give you like a verbal score, that's unidimensional, right? Like they're trying to make it unidimensional. There's nothing that says that you couldn't report more than one dimension, but you would have to measure each dimension reliably enough to be able to do that. And that's one of the biggest problems with the GRE is that they don't give you standard errors of measurement as part of your report. So how reliable it is like, who knows? So does anyone have any other background info on GRE? Is this something that you talk about in any of the other measurement classes? No. Okay. Yeah, sorry, I can't be more help. But I do know that their guide to interpreting test scores has some information in it, but it's pretty vague with respect to like the estimation and model refinement process.
So it sounds like you're saying that because you're like, if it were me doing it, you might do it differently than.
Well, there is, I think, in the IRT world, there's sort of an assumption that everything has to be unidimensional. Like if you think about like just the names of things, like there is a phrase multidimensional IRT, for instance, and that refers to models in which there's more than one theta. Oftentimes, those are exploratory models where every item is thought to measure every theta, and they have the same problems as exploratory factor analysis. But the idea that you would need an adjective of multidimensional, right? Like when we had CFA, it wasn't multidimensional CFA versus regular CFA. We had multiple dimensions as part of it. You can have more than one dimension. There's absolutely no reason why you can't. And they can be correlated or not. It's your choice. Odds are good that they would be, right? If you have like one test that's measuring more than one thing. The catch is that estimation is a lot harder because there's not a multivariate normal distribution that underlies this whole process. What you have is a Bernoulli distribution for the items paired with the multivariate normal that goes with the thetas. And when you put those two things together, that's not one like known distribution the way that multivariate normal is. So that's the end of this lecture, is talking about what a pain in the ass estimation is. And I think that's the reason in practice, besides differences in reliability, that if you only have so much time to give items, then you have a choice. Do you want to measure one thing really well, or do you want to measure two things so-so? And one thing really well, I think, corresponds to what people need in terms of test scores and whatnot in practice. But in the context of, say, research, there's no reason why you can't have more than one theta. It just will take M plus longer to work with it. If you use full information maximum likelihood, that is.
That helps a lot. Thanks.
Sure. Other questions? Thoughts? All right. Then let me figure out where we're starting. Slide 38. Item and test information. That's where we are. Reliability and why it's different now than it has been before. The idea that reliability is now conditional. That's the big change. All right, so let me move this thingy out of the way. All right, so we talked about this a little bit last time, I think, but the idea of giving our imaginary variable a scale. Remember that in CFA? We got to do that again. I'm gesturing at my other monitor. Sorry, I know that makes no sense to you guys. But we call it anchoring in IRT, but it's the same thing. Um, the most common approach is to set the scale of the model by fixing theta's mean to 0 and its variance of 1. An alternative is to use like a marker item, and you would fix its A to 1 and its B to 0. And there's other combinations possible too. You could fix the mean item difficulty across all the items to 0. There's other approaches used, but it's the exact same problem because ultimately theta doesn't exist. Theta is a latent variable, and so for that reason we have to give it a scale. And once we do that, all of the other parameters for the items can be found in relation to that. So if I'm doing the GRE, rather than fixing theta's mean to 0, I could fix theta's mean to 150. Right? And rather than fixing the variance to 1, I could fix the variance to 100, since I think the standard deviation is supposed to be 10, something like that. So it doesn't matter what numbers you choose, so long as theta has a mean and theta has a variance. And we'll continue in the current practice that I asked you to do in homework 3, and you can assume for the next several weeks that theta has a mean of 0 and a variance of 1 in terms of the scale. That way we know what a unit change is in interpreting the slopes. All right, so information. The idea of reliability has a new name. It's called information, but it's the same damn thing. In confirmatory factor analysis, when we talked about how do you know if an item is good, right? In confirmatory factor analysis, you have an effect size for each item that's the standardized loading. It tells you in a correlation metric how related the trait predictor is to the item response, and items that have stronger standardized loadings are better items. Well, we can also compute something that's known as information, how much information the item contains with respect to the trait, as unstandardized loading divided by error variance. And the thing about information in confirmatory factor analysis is that, like the standardized slope, it's going to be constant. So the fact that there is a linear relationship between the trait and the item response means that the amount of information an item contains is the same at all points along the trait. If an item is a good item, it's good for everybody. That is not the case in IRT because it's not a linear relationship between the trait and the item response. It's a nonlinear relationship. So back in the world of CFA, so this is from the forgiveness of situations example. I've got item 1 and I've got item 6. And you guys got a chance to make these plots for homework 3, right? Did you see that your predicted responses go out of bounds? Yep. Yeah, it's very rarely the case that I've seen people's projects where they don't. And that was the case here. So the x-axis has meaning because of the scaling of the model such that the trait has a variance of 1. So what I'm plotting here is plus or minus 3 standard deviations. And I have purple bars to indicate where the item boundaries are. So the lowest you can have is a 1 and the highest you can have is a 7 in this example. And so this is what the factor model says should happen. So I've got the unstandardized solution here for item 6 on the top. It has an intercept of 5, so at a factor score of 0, that's the expected item response. 0.82 is the slope, so that's the change in the item response for a 1-unit change in the factor, so per standard deviation. And it had an error variance of 1.67. Same information for item 1. It has a stronger slope and a little bit less error variance. I can use those quantities, the unstandardized loading squared divided by the error variance, to compute information. And here are the standardized loadings that correspond to the unstandardized loadings. And it looks like item 1 is stronger than item 6. Cool. So let's talk about how information then translates into reliability. So information, for instance, I have no idea of interpreting these numbers, these 0.4, this 1. I can tell you which item has more information in it. Item 1 has more information than item 6, and I know that because of these numbers, but I also already knew that because of the standardized loadings. So in the idea of CFA, we didn't need information because the amount of the strength of the relationship and sort of an absolute effect size was given by the standardized loadings. But to be able to interpret these numbers, I can actually convert information into a traditional reliability metric. And the conversion is very straightforward. Information divided by information plus 1 gets you reliability. And that derivation is shown here, where that comes from. But the big point of the story here is that this idea of how much information an item contains is going to vary across the trait in IRT, whereas it does not in CFA. So if I compare the plot that I just showed you here, like a CFA type plot, CFA is a linear model. There is a linear slope that connects the factor, the latent trait is the predictor, and how that factor predicts an item response on the y-axis. The analog are these curves that we've seen here in the context of binary items. So if I were to plot the amount of information in each of these items as a function of the trait. So the red and blue lines that are shown here demonstrating the slope in a CFA model would look like this if the y-axis was information. So information for item 1 is higher than information for item 6. That's because item 1 has a stronger factor loading than item 6, and it's a stronger factor loading, period. So these information functions are flat for these items. That is not the case for the items from the binary model. So if we zero in, say, on these pink items right here, these pink items have a difficulty level of 0. So that's the point at which they cross the 50-50 mark. Here are the information functions that result from these two items in particular. And I want to point out two things. One is that information functions are relatively highest at 0 because that is where the slope of this nonlinear logistic function is the strongest, at 0. So at the 0 on the theta scale, that's where they have the most information. If I were to compare the two items, I see that the pink item has more information at that point, and that's because it has the stronger slope of the two. So these two items become much less informative as you move away from their difficulty location. So question from the audience. So if you were to compare the blue items, then the highest would be at -1. Exactly. So if I put the blue items on the same picture, they would peak at -1, and the information function would fall away. So what's going to happen is that the total amount of reliability in your set of items, because each item contributes at a different point, it contributes a different amount at a different point, we're going to end up with a function that describes the total reliability of the scale in terms of the information that the set of items gives you. And that is how we think about reliability in these models. It's not one number anymore. It's a function. It was one number in CFA because each of the item's information functions was flat. And the reason it was flat is because CFA is a linear model. If an item is good, it's good for everybody to the same extent. In IRT, if an item is good, it's good for people at that difficulty location. So difficulty matters. So here's some pictures. So these are item characteristic curves that vary in where their difficulties are. So I've got a set at -1 here. I've got another set at 0, set at 1, and a set at 2. And then within each set, one of them has a slope of 1 and one of them has a slope of 0.5. So each of these items then should be thought of as for a specific kind of person. The blue and green items out here, they are designed to measure people with really high levels of theta well. That's what they're for. And as we move to the left, we get the items that are designed for people with less of a trait. So in thinking about what items to include, you have to ask yourself, who am I trying to measure? Do I want to really fine-grain differentiate people of high abilities? Because this set of items isn't going to do that. Do I want to try to measure everybody well and nobody super well? If that's what I'm trying to do, this set of items would be an okay choice because we're trying to cover the whole spectrum here. Those item characteristic curves translate into information functions that look like this. So if we zero in, say, on blue and green out here at 2, their information functions, here's the green one, and here's the blue one. The blue item has a lot more information at its difficulty level because it has a higher slope. That's what the slope means. There's a stronger relationship to the trait. The item has more information to contribute. So all things being equal, if I'm trying to make a short form, I want the tall items. If I have to pick between, say, the green item and the blue item because they're both designed to measure high theta people, I want the blue one because it has more information. And if we take all of these curves and add them together, like literally add them together, the total height that results has a special name, and it's what's known as test information. I think you can call it something else information if you're not doing in an academic setting, but test information is the conventional term. It's the sum total of all of the information that you have across your items, and it is a function of theta. There is an inverse relationship between test information, for instance, this blue line, and what the standard error works out to be for your predicted thetas in your sample. So where you have the most information, standard errors for people in that range are going to be the smallest. And where you have the least information, standard errors are going to be the largest. So it's not sufficient anymore to say, oh, I have reliability of 0.8, right? Where do you have 0.8? You could have reliability of 0.8 in the middle, but you don't have 0.8 over here necessarily. And this is where this y-axis in terms of information is very hard to interpret, and converting that y-axis to reliability will make it easier for your readers to understand. So let me give you a couple examples. This is a test information function that was found in my dissertation. So welcome back to 2003, folks. I'm going to make fun of myself here for a few minutes. Is that okay? Because you know what? There's only 2 kinds of dissertations in the world. Do you know what those 2 kinds are? No one's told you this? Okay. Yes, Kelly says one kind is done, the other kind is not done. Those are the only distinctions that matter. That's it. And you know what kind of dissertation this is that I'm going to make fun of in this lecture and in the next few lectures? The done kind. So before I make fun of myself, let me catch another question. Is it inverse because information is where there's less error or because it is more precise? So question on this, the formula for the formula for standard error is literally based in test information. So that's where standard errors come from, is the test information function. So there's a one-to-one correspondence there. So they're telling you the same thing, just in a different metric. Standard errors are highest where test information is smallest. But the question is, how much test information do you need to get a decent standard error? Like, how precise do you want to be? So let me make fun of this. So the reason that I made this picture, and by the way, this picture went into my job talk. Okay, that's how proud I was of this stupid picture. And the goal of my dissertation, so once upon a time, I was in the world of cognitive psychology and cognitive aging. And the goal of my dissertation was to make an instrument to measure selective attention capability in older adults, and to then use that instrument as a predictor of simulator driving impairment. So that was the goal of my dissertation. It was actually funded by a grant from State Farm Insurance that they gave me to do the project. So I had older adults come into the Kansas City Medical Center, where they had this really crappy but free driving simulator. And so they drove in the simulator, and I gave them a battery of tests, including this new measure. And lo and behold, my measure actually predicted their performance in the driving simulator, so I win. So I was very excited about that, and I was actually able to publish that result, even though this picture is not good. So the point of this picture was the idea is that the goal of this instrument was to measure older adults who are likely to have problems, who have deficits in selective attention, people who probably shouldn't be driving. Like, that was the goal. So I looked at the shape of this thing and I went, nailed it. Because my information is highest on the lower end of the scale. That's where I want to have the most sensitivity. My information dips quite a bit on the high end, but that's okay because those people are fine. Like, if you're with it, I don't need to know how with it you are. Like, my goal was not to measure high functioning people. It was to be able to find the people who might have deficits, right? So that was the point of the slide. It wasn't until I started teaching this material like a decade later that I looked at this y-axis and went, huh, shit. So I have information that peaks at just under 2. Is that good? If I wanted to talk about this in terms of reliability, it's information divided by information plus 1. In other words, the maximum level of reliability at any point in my scale is less than 0.67. Oops. So my test actually sort of sucks. But done kind. That's all that matters. So question, how do you call this the standard error? The standard error of the estimate or the standard error of the measurement? So good question. These are standard errors of the trait. So once you have your model parameters for the items, you can reverse engineer a prediction for what theta is most likely to be for each person. Theta is not a model parameter, but you can generate a predicted theta and the standard errors of those predicted thetas. So you can think of it as a standard error of measurement. They are a function of test information. The item parameters are also going to have standard errors for how well they are measured. So like if I say the difficulty is -1, well, what's the standard error around that? Could the difficulty actually be -2? Or is it really close to -1? Like, how much wiggle would you expect to see across samples? That the general idea of standard error is how far off is the sample version of something on average from the population version. So the item parameters are going to have standard errors too. And how good those are is a function of how many people you have at that point with which to nail down just how difficult the item is. So the reason that this information function looks the way it is a consequence of the items that I had. I had a lot of items that were on the easy side. I did not have a lot of items on the hard side. So because I didn't have a lot of hard items, I don't have a very good shot at measuring high people. And for that same reason, because I don't have the number of high people that I have is going to dictate how well those item parameters are estimated, how variable they would be expected to be. Was the estimate theta based on maximum likelihood estimation? Yes. Wouldn't it be the reciprocal of theta squared? Yeah, whatever the formula is, they're inversely related here. So standard errors come from test information and they're inversely related. We'll talk about estimation later on, but yes, it comes from a process I'll describe to you called marginal maximum likelihood, which is maximum likelihood where we have to integrate theta out of the likelihood in order to find the estimated model parameters. It's tricky. So, point of the story though, where your items are located in terms of their difficulty lends itself to creating this function. So you can control where your measurement is sensitive and where it's not by the kinds of items that you choose. And if two items have the same level of difficulty, the one with the higher slope, the A parameter, the one with more discrimination, is going to contribute more information. Okay. Here's an alternative. What if the goal of measurement was to group people, to identify students who should be part of a gifted and talented program, for instance? If that's my goal, then I might want an information function that looks something like this, where I've maximized information around the point where I want to designate people as to either being qualified for this group or not. If you're not going to be qualified, I don't need to know how low you are. However, if your goal is classification, if what you plan to do once you get your trait estimates is to find some sort of cut point and then group people based on that cut point, you do not need an IRT model. Because going to the trouble to measure all the different possible levels of theta and then discretize that information into just there or not or something like that is a waste of time. If your goal is classification, then you need a different kind of latent trait model, which is known as a diagnostic classification model, also known as a cognitive diagnosis model. And in those models, your trait is already categorical. So like the theta would be whether or not you should be in gifted and talented as the theta. And the model is designed to maximize that cut point specifically. So just to put that out there, I don't know when that class is coming back, but it should be offered again, hopefully within the next few semesters. All right, have I answered all the questions? I think I've caught up with the chat. Other questions or thoughts from you guys? Running low on rocket fuel.
Well, I kind of had a question when you were explaining why your test wasn't good, because it was like you did explain that you intended to measure people low on the trait. So in theory, it seemed like it would be a good idea, but it wasn't a good idea because, is it because if you do have people high in the trait, you can't discriminate between, you can't decide who's high or low? I maybe don't understand that part of it.
Okay. The shape of this thing is good.
Yeah.
The shape of this thing is consistent with what I wanted to do, which was to measure people that have deficits well, and I'm less concerned about measuring people who are fine. I don't care how fine you are if you're fine. So from that perspective, that was why I made the picture, and that was the point that I made when I presented the picture. The reason that I'm mocking myself now and why this actually isn't a good picture is the y-axis.
Oh, sorry, I missed that part.
Yeah. And it's because information is this weird metric where it's like, is 2 good? I have no idea, right? But actually, I do know. You can convert information into reliability as information divided by information plus 1. And that goes between 0 and 1 with the traditional interpretation. So what that means is that if I had wanted to hit 80% reliability, then I should have had an information function that goes up to 4.
Okay.
So it's like my test is not measuring anybody well, but of the relatively least shitty part, it measured the people I wanted to, like least shittily. if I can use that as an adverb. It's least
Thank you for
shitty.
going back. Sorry.
Yes, no, thank you for asking. I appreciate the questions. If I didn't want you guys to ask questions, we wouldn't be meeting synchronously. Otherwise, I'd be lecturing to my computer in my pajamas. And that would be a lot less fun. Okay, so other questions or clarifications. So the big idea is that it's no longer one number for reliability. If you see one number for reliability, what they have done is marginalize over theta. So for instance, I could take this function and overlay a histogram of my best theta estimates for each person. And I would be like, okay, so I've got, say, 3 people at -3, and so their reliability is this, plus 4 people at -2.5, and their reliability is this, plus more people at this, and it would be a weighted function. So if you see one number for reliability, odds are good what they did is weight the information function with the number of people who are estimated at that point, and they came up with one number as a result of that process. To me, that is not helpful information because it doesn't tell you about the potential mismatch of what you're trying to do and what your function looks like. All right, so the idea that not every item works for everybody is a consequence of the nonlinear model. And so we can't just look at factor loadings and decide whether or not an item is good. And we can't just select items based on their factor loadings like we could in CFA. We have to know where they're good. And so items that have extreme levels of difficulty, so the ones that are designed for super high or super low people, they may have low loadings, low slopes, because there's not a lot of people out there. But doesn't mean we wouldn't, it means that doesn't mean we should dump them. Let me put it that way. We should keep them if we want to measure low people or high people. We need those items. Question. The one number used for reliability, is that what is usually shared in publications? Sometimes. That's not what I do. What I have coached people to do is to give the range of the trait at which a chosen level of reliability is met. So for instance, I might say something like reliability was 0.8 or greater between -2 and +2 or something like that. Since you can't usually give the function, I try to summarize the function. If reviewers want a measure of reliability, then you could give them the averaged over version. It's not something that M+ provides, but you could probably reverse engineer it or ask for it from some other program. All right. Other questions? Okay, so we hit this point. This picture is from your textbook. There is an error in the legend, but they are contrasting the idea of fixed test versus adaptive tests of different lengths. So in general, you would expect that a test that has more items, or an instrument that has more questions, would measure better, but that's not necessarily the case. The whole idea of computer adaptive testing is to only administer items that have information where you need it. So if you start somebody in the middle and they get the item right, for instance, in binary data, you'd give them a harder item. If they get that one right, you give them an even harder item. If they get it wrong, you back them down to an easier item, and you can wiggle around until you get to that point. And so if you're able to customize which items you're giving somebody, then potentially you don't need as many to get a decent standard error. And so this plot is the standard error of measurement for theta as a function of two different tests that she's comparing. The fixed test standard error is the lowest in the middle, where there's the most information in this example, and standard errors get really high on the outside. Whereas for an adaptive test, if you're able to pick only items that are relevant, you can maintain standard errors that are relatively flat. that are good across the trait. All right. So this idea that you don't necessarily need to give everyone every item, this is a really good thing. So adaptive testing is an extreme case of that, but this property can be used advantageously to make sure that you're still measuring people well, even if they're changing. So anytime that you are fitting a measurement model where there are separate parameters in the model for your trait and separate parameters for your items, you can do this. So this idea of linking forms together, the idea that not everybody has to take every item, that's a very common thing people talk about in IRT, but it's exactly the same case in CFA. So you can use this property to your advantage. For instance, if you're trying to measure an ability in children and children are growing, well, you need to change the test to be able to keep it sensitive as they get older, but at the same time, you can't measure change if you don't have overlap. Here's what you don't want to do. You don't want to pick a test for kindergarten and then pick a different test for first grade and then pick a different test for second grade. You're screwed. There's no way to put that back together again. But if you weave things in, then you can calibrate everybody onto the same trait and all the items onto the same trait, even if not everybody has every item. So for instance, if I have the first occasion where people are at the lowest level of ability, I give them 3 easy items and 3 what are known as linking items or anchoring items that are designated for overlap. I might drop some of the easier items and pick up some harder items at the second occasion and continue doing that as I move along. So given sufficient overlap of the items across occasions and across the samples, you should be able to piece this thing back together again. The only catch is that you would have to find evidence for the fact that these items 4, 5, and 6 act the same way across time, that they are invariant, that they would have the same difficulty and discrimination at any occasion. Because what you're going to do is sort of use them as the anchor point and add all these other items onto the same trait, believing that they are the things that define the trait equally across occasions. So I once was in a helping with a research project where they did this. They gave a different test every year. And do you know what the PI told me? Well, we're just going to convert them to z-scores. And that solves the problem that they're different tests. My response? Z-scores don't grow. Don't do that. So you can deal with accidental linking forms this way. So for instance, if somebody changes something halfway through a survey, they change which items are given or they change which response options. If there's overlap, then you can link it back together again. What you can do is fit a model where everything is being estimated simultaneously. And if you have your items that are invariant that have the overlap, then you should be able to put it all back together again. But the key is the overlap. That's the most important thing.
Can I ask a question?
Yeah, please do.
I don't know if I should I do the raising hand? Should we be doing the raising hand thing?
No, just talk.
So I realize it'd be different for every situation, but what things would you look at to figure out how many items you need in to be similar across the forms?
Oh, technically you need 1.
Hmm.
Mathematically, you can pull this off with 1 common item, but you better believe that item is the best item in the history of the world to do that. That's a really great question that I don't think there's going to be one answer to, but you would want to make sure that you have enough items in common that if some of them were not invariant, that you'd still be able to pull this off. Because you have to believe that they're working the same way in each sample or in each occasion in order to do that. So, yeah, I don't have a good answer for you. I think trial and error would be would be part of the story. The more items you have, the longer it takes, the better things go. So there's always going to be some balance of like, what's the fewest items I can get away with and not have this thing fall apart. Um, but I think this property is not as well known outside of education. So I wrote a paper basically describing that you could do this in the context of the Peabody Picture Vocabulary Test because they changed forms over time and to try and help researchers who might have Form A with one sample and Form B with another sample. They changed tests in addition to having more than one form on a test. And so I did a project trying to calibrate all that stuff and demonstrate how that would work. And I have a couple examples also to follow that I got from elsewhere, but I think it's one of those attributes of this that's not as well appreciated as it could be. So, are you in your project, are you guys dealing with this issue? How many to put in common?
Yeah, I think right now they have like 4 out of 18 maybe, but I see what you say about like trial and error. And so it's like, it's hard working with real people to get the time and the preparation for the trial and error part.
Yeah, and it also depends on how good those 4 are. It depends on where they're located. So, yeah, there's a lot of variables that would have to be considered simultaneously. Question: what if you have reason to believe that a latent trait changes across years and requires different questions to address this change? Would you still need overlapping questions? If you want to make comparisons across time involving the trait, then yes. Like if you want to say that depression increases during adolescence, right? And how an 11-year-old behaves if they're depressed is different than how an 18-year-old behaves if they're depressed. If you want to be able to make comparisons involving the trait, you need to have overlap. There is a paper coming a couple weeks when we talk about invariance that makes an argument that even the common items don't necessarily have to be held invariant. They draw an example from the child behavior checklist, I think. There is items on there that describe externalizing and deviant behavior. For instance, if you're measuring children, let's say from ages 3 to 18, one of the items is how often does your child bite other people? I don't know if you've been around any 3-year-olds, but they sometimes bite. Like they don't have the verbal skills to explain that they're pissed at you, so they might just try to bite you, right? If an 18-year-old bites someone, that is a very different type of problem. So they use that as an example to say, hey, look, biting is not going to be invariant over time because it means something different. And you could just let it be one of the items that even if it's the same item, you would let its characteristics and difficulty and discrimination change over time as if it became a different item because functionally it is. So there's some amount of sort of theoretical reasoning that has to be applied to think about whether or not the items really do mean the same thing, but there has to be some common ground for the linking. There has to be at least some items that do mean the same thing over time in order to pull this off, to be able to talk about trait comparisons. Okay, so here's another example. This came from a talk that I attended as a graduate student a long time ago, so I don't have a source for this, but I really like this example. One of the situations in which this can be helpful is if you're trying to decide which measure to give to a sample, if there's more than one that's possible. So the context of this example is measures of physical capability. There is one scale that is used called the SF36. I can't remember what SF stands for, but it tends to be used in general populations, so just like your average adult. And they have questions on there that correspond to vigorous activities and moderate activities and so forth. And the lowest items on the scale would be things like you need help bending or bathing and that kind of stuff. In contrast, if you're trying to measure physical functioning in populations with disability, then most of those items on the SF36 are going to be way beyond what they're capable of, and they need a lot more easier items. And so there's a checklist that's known as the Activities of Daily Living that has items on it about individual just care, basically the lowest levels of functioning. So if you were trying to decide, which of these scales do I give in my sample, you don't necessarily have to just pick one or the other. There's nothing that stops you from picking the items from each that would be most appropriate for what you're doing. So if you don't have room to give both of these in your protocol, don't just pick one and have a ceiling effect. Don't just pick the other and have a floor effect. Get some items from both and build your own ruler. And so that's the point that they're trying to make here. You can mix and match items from different questionnaires. You can create a new measure. There's nothing that stops you from that because we don't have to have a total score. We're not adding things up. We're coming up with a latent metric that characterizes all the items and all the people. So you can borrow across instruments to try and do a better job than what any one instrument might do. There's an article on your reference list about this as well, and I have a couple pictures coming up on that. All right, let me pause. So, questions, thoughts on this example? Oh, that changes things. Yeah, there's lots of instances in which the way that someone has measured something may not be how you would have done it or what you need. And I do not think you are beholden to someone else's choices. I think you can make up whatever you want, and you have the power. You can create your own new scale out of items that make the most sense for what you're trying to do. Absolutely. Another reason to go through this process, even if you're just working with one scale, is the idea that the relationship between basically the scale of theta is supposed to be a linear scale, whereas when you add shit up, those items are actually ordinal. And so the relationship to the trait then is squishier. And to make this point, there is, this is a paper that's on your reading list. I think they did a nice job of explaining this. And so they're trying to compute an overall test curve for a measure of the mini mental status exam, which is used as a cognitive screener. And on the y-axis is the sum of the items from this test, and on the x-axis is the measure of theta. And so this type of relationship is pretty common, where you see that the theta can keep going, but the sum score doesn't. And so there's compression along the extremes of this trait. Let me check for the question here. If I choose to change some vocabulary in a scale, it would be a different scale, right? Yeah, I think so. If you change the wording of the items, but that's not necessarily a problem. You can say that you changed it and that you did the appropriate psychometric analyses that support that the items still work the way that you had intended, or maybe they work better. I don't ever recommend taking someone's scale and using it without testing it on your sample. I think that psychometric analysis of your scale is always necessary, even if it's an established measure, because you never know what it's going to look like on your people. So if I have something like this here, for instance, on the theta metric on the x-axis, I could have a difference that's 2 standard deviations that corresponds to a 5-point change. But elsewhere on the same scale, I could have half of a standard deviation correspond to a 5-point difference. So this becomes problematic if you're trying to do change scores, make group mean comparisons, and that kind of thing. So what they did in this paper is show how to combine items from 3 different measures to try and improve measurement, try to get this curve basically as close to a line as possible. And after they did so, it looks like there's only this compression at the top of it, and that was because they didn't have enough items at the very top to make sure that the linear relationship between the trait and the sum score was maintained. So the sky is your limit in terms of combining items into stuff. All right, so changing gears in a second, but the main point, an item is not necessarily a good item. It's good at a certain point. That's the thing I want you to hang on to. And so in the example that I'm going to show you, we will see what happens to the trait estimates and their standard errors when you don't have enough items to cover the entire range of the trait. You can see it happen. All right. Are you ready for this to turn into factor analysis? Okay, it's going to happen. So let me show you how this works, because I have to explain this part before I can show you the example in M+. So earlier in the semester, I used the analogy that a CFA model, such as shown here, is the same thing as linear regression, except that we have a predictor that is latent instead of a predictor that is observed, right? You willing to buy that still? So there's a shift in the notation. A typical regression model uses betas for the fixed effects. So beta 0 for the intercept corresponds to the mu for the intercept in the CFA model. Beta 1 for the slope of the predictor corresponds to lambda. And instead of x, I'm calling this f because it stands for factor. But otherwise, it looks pretty much the same. And then I told you that IRT and models are like logistic regression. But if you look at the logistic regression equation and the 2PL that we've been talking about, they look nothing alike. So let me show you how to get from one to the other. So binary regression models look a lot more like factor analysis models. Hang on here. This thing always moves over. 1 second. Come back. No, it won't let me fix it. 1 moment. Come on, you can do it. Exit. There we go. 1 second, folks. I have to fix this thing tabbing over all the time. Do you ever have that where you fix something and like the next time you come back, it's not fixed anymore? There's certain pieces of my slides that do this. They go from left aligned to center aligned, and I cannot figure out why. But I know where they are, and so I know to watch for them. And it doesn't matter which version of PowerPoint, it seems to always do this. And it's this one right here, the ogive. Ogive wants to move over. It's supposed to be left aligned.
Sometimes Word does this and it just does everything as a global effect rather than a local effect. So what you need to do is do Control Z in Word. I learned that. It gets annoying, but fun fact.
Okay, so for the formatting?
Mm-hmm.
Good to know. But there, now it looks like it's supposed to. Okay. And there. So let me introduce you to IRT as a factor analysis model. It's this right here. So lambda's back. Lambda is our slope. F is back. Why? Because F theta, see, that's a stats joke. No? Not having it today? Okay. Well, F that. F stands for factor. Now this thing, rather than having an intercept, we have this stupid thing. This is my nemesis. This is called a threshold. So we have to get from this IRT model into this version of the model, and I'll show you how to get there in just a minute. But if we're going to talk about this version of the model, then we have to redefine our parameters. So the loading is exactly the same as it was before. It is the change in y for a 1 unit change in x, because it's a slope. The only catch is that change in y refers to the linked version of y. So either the logit or the probit. And so as f goes up by 1, the loading says what happens to the predicted logit or probit. This thing right here is the opposite of an intercept. It is a threshold because of the minus sign. So an intercept is the expected outcome when your predictor is 0. So when f is 0, the intercept gave you the predicted item response. What we're predicting right now is the probability of a 1. If I stick the minus sign on front here, it becomes the probability of 0 instead, because logits are symmetric. So if I have the probability of a 1 corresponds, say, to a logit of 2.2, the probability of a 0 corresponds to a logit of negative 2.2. So when we estimate these models in M+, this is what it's going to give us. It's going to give us this stupid threshold thing and a factor loading. Now here's how to get from that back to where we were. Ta-da! Algebra. Here's the conversion. It works out that the factor loading is the same thing as A. A times B is the same thing as a threshold. And here are the conversion formulas to get back and forth. So we can talk about our model parameters for the items in two different ways. We can talk about them using A's and B's, or we can talk about them using thresholds and loadings. A is to loading, B is to threshold. And they tell you slightly different things. Each of them has a different reference point. So let me do, in the interest of time, I'm going to skip ahead and show you the picture that I like.
Is B by itself threshold, or did you say A times B is the same thing as the threshold? Like tau was threshold, right?
Tau is threshold and A times B is tau.
Okay.
Yep, the minus sign sits out front to be consistent with the direction of B because it's theta minus B in the IRT equation.
Mm-hmm.
So yeah, go ahead.
What's B by itself in this context? What is that, theta over the, like I know A is the loading, and then A times B is the threshold. What's B by itself?
B is the same B from the IRT item difficulty.
Okay.
So if you wanted to, here we go. If you have loadings and thresholds, then you can use those to get A's and B's. If you have A's and B's, you can use those to get loadings and thresholds.
Thank you.
Yeah, so in these models, theta variance is fixed to 1. So A is the same thing as loading. And theta mean is fixed to 0. And theta variance is 1. And so the second term drops in here, and the threshold is just A times B. So what's going to happen is that M+ is going to estimate loadings and thresholds and then turn them into A's and B's for us. And I wish I could make this easier, but I can't. Because if you fit these models, say, in R and using their IRT packages, some of them give you intercepts and slopes. Some of them give you thresholds and slopes. Some of them give you A's and B's. And so it gets very tricky to figure out what the hell you have. But let me show you how these things all relate to each other because they're converging onto the same ideas. So here's an item characteristic curve from one of the items in the example that we're going to show. And so as a reminder, here's how these things all relate to each other. I can talk about the predicted logit of the probability of a 1 in terms of intercepts and loadings. I can talk about that same predicted logit in terms of thresholds and loadings, or I can talk about it in terms of discriminations and difficulties. So on this curve, the point where the curve crosses 50-50, that is my that's my slope right here. So that's discrimination, that's my factor loading, that's the same thing. It's the slope at that point. Okay, so that's A, and loading. B is difficulty. B corresponds to the amount of trait needed to get to that 50-50 mark. So B is relative to where 50-50 is in probability. B is relative to where 0 is in logits and probits. So the reference point for what B means is it's the point where the predicted outcome in logit space goes to 0. That's where we've been so far. The intercept loading version has a different anchor point for where we are on the x-axis. So for instance, for this item, the intercept was estimated at 1.6 because the intercept is referring to where theta is 0 as the predictor. The intercept is the expected response when predictors are 0. So the intercept gives you predicted response in logits where theta is 0, which happens up here. And so if I unlogit that, a logit of 1.6 corresponds to a probability of a 1 of 0.8. If I take that intercept and multiply it by -1, now I've got a threshold. And if the intercept gave me the probability of a 1 when theta is 0, the threshold gives me the probability of a 0 when theta is 0. So intercepts, thresholds, and Bs all are talking about location. They differ in location of what? B is the location where the logit is 0. The intercept is the predicted logit when theta is 0. And to be consistent with the direction, because higher intercepts would correspond to easier items, that's why they give you the threshold, which is -1 times the intercept. So the bottom line is that when you're estimating these models in different software packages, you need to read the documentation very carefully to figure out what the hell they've given you. Have they given you thresholds? Have they given you intercepts? Have they given you Bs? Because they're related to each other, but they're not the same thing. And so what M+ estimates directly are thresholds and loadings. You can ask it to also spit out the corresponding A's and B's. So loading and A are the same thing. In terms of location parameters, I think B is far more useful than intercepts or loadings. And that's why I teach the IRT side first, because I think of that parameter as much more informative. And we'll look at an example in M+ that will help illustrate why I have that opinion. I hate thresholds. Hate! That's a quote from Chappelle's show. He once went to the player haters ball where they all chanted hate, 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 hate. So that's my opinion of thresholds. Hate. In M+, the threshold parameters are going to show up on your output with $signs next to them. No joke. Like $1, $2, $3. And I think it's because if you ever understand what the hell a threshold is, someone will pay you. They're the money parameter. Even Linda Mutane dodges explanations on the comment boards. People ask her what a threshold is, and she says, it's usually not interpreted. That's her response. That's how much she hates thresholds. So we'll see an example that helps to put all of these concepts together, but now you can believe me that what we're secretly doing is factor analysis still. All right, so questions as we wrap up. That means we get to start an example next time, and I'll show you all this stuff. All right, let me know if you need anything. Office hours start now. Otherwise, peace out.